So here in this chapter we are studying the sampling distribution. Okay, so we think about the population, which was the very first definition that we learned, and then we learned about the sample, which we obtain as a kind of subset from our population or entire population, and then we considered their mean and the variance. Okay, and then in this chapter we are basically studying what kind of distributions each of this mean and the variance are following. Okay, so in the first case, in this kind of theorem, which is called the central limit theorem, we think about the mean. Okay, and I gave an example of like a surveying company. So each surveying company collects maybe 50 different people's height, and then they compute their own mean, and then these mean values are following some distribution, and that distribution is determined or described by this central limit theorem. And this central limit theorem is saying this mean value. Let's see. Give me just 1 second. Okay, so back to the central limit theorem. So we talk about the mean value from our sample, and then this mean value or this x bar is following basically the normal distribution. So your population, I mean, it doesn't matter whether your population is following the normal distribution or not. But for whatever distribution that you have for individual people, once you obtain this sample mean from 500 different surveying companies, and then the distribution for these sample means are following the normal distribution, and its mean and the variance is as follows. So the mean is the same as the true mean of individual people in your population, and then the variance is defined in this way. So basically the true standard deviation of individual people's height, and then it's divided by the square root n. So that way, given your true standard deviation, it gets smaller and smaller as you have more and more sample size. But here the point is that you basically have normal distribution for your sample mean. Okay, and then once you normalize, or once you transform your sample mean by subtracting the true mean and then divide it by its standard deviation, and then we call that random variable as z. And after this transformation, basically z is following just the standard normal distribution, which has zero mean and the unit variance. By the way, the unit mean the unit means just 1. Okay, so unit variance means the variance is just 1. Okay, and then there was an extended version of this central limit theorem when considering the two different population, and each surveying company obtains n1 samples from one population, and then n2 samples from the other population. And then we considered the difference of these sample means from these two samples. And then also each surveying company will have their own x1 bar minus x2 bar, and then this value will also follow the normal distribution that has the mean of the difference between the true mean and then the summation of each of this variance from each of these sample means. Okay, then we kind of stopped at this point. So we consider the sample mean. So again, each surveying company collects maybe 500, or each surveying company collects maybe 100 samples. And then we considered their sample means. And then if we have 500 different companies, and then we have 5 different sample mean values. and then we consider the distribution of it. But now we can think about the sample variance that each surveying company computes. So again, we have different surveying company A, B, and C, and so on. And then each surveying company will collect maybe 100 samples. And B will also collect another set of 100 samples. And then previously, when talking about the central limit theorem, we considered the mean value from each company. But in this case, we consider the sample variance that each company computes. And then if we recall the definition of the sample mean, it is defined in this manner. Okay? And so in this case, so company A collected 100 samples, and then they computed their own sample variance. And then B will also compute their own sample variance. And then for those different sample variances, so if we have 500 different companies, and then we have 5 different values for this sample variance. And then when considering their distribution among these 500 different values, what will be the distribution for those values? Okay? So we talk about this kind of distribution. Okay? And then this distribution is basically following, the answer is that they follow this chi-square distribution. Okay? And then chi-square distribution has just only one parameter, V, right? And alpha was, and now I can memorize it. So it is defined as this. And beta is set as 2 in the gamma distribution. And that is what we call chi-square distribution. Okay? And then and here in this case, if we considered 100 samples, so each surveying company collected 100 samples, and then we considered the sample variance computed by company A, company B, and so on, collecting those values, and then we just think of their distribution, and then this one becomes this chi-square distribution with the degree of 99. Okay, so this chi-square distribution has the parameter V as 99. Okay, and then we let's see. Yeah, we studied a little bit on the last part in the chapter 7. Okay, so we talked about the physical meaning about the chi-square distribution. So basically, chi-square distribution. So suppose we have a chi-square distribution. So typically that is denoted as this. So yeah, this is called chi, and then this is a squared, right? So that's why we call that as chi-square distribution. And it has a little bit of a meaning. And this meaning is actually considering the squared number. And that number is basically the standard, the random variable from standard normal distribution. Okay, and then we basically square of it, take the square of it, and then consider the summation of it. So, so basically we consider multiple standard normal random variables. So suppose we have, usually standard normal random variable is denoted as this Z, and then person 1 obtained his own sample from standard normal distribution. So this guy, the Zi is following normal distribution of 0 and unit variance. Okay, in this case, person 1 obtained Z1, and then person 2 obtained Z2, and so on. And then we have, for example, in total 10 people, and so we obtained 10 different sample values from standard normal distribution. Okay, so each of these Z1, 2, and Z10 will have 0 mean and the unit variance. But also, they have these kind of same distribution, but at the same time, they are independent of each other. So when sampling Z2, it's not dependent on Z1 or Z3 and so on. Okay, So that condition is called, yeah, so probably you will see this kind of notation of IID. Okay, it's a independent and identically distributed random variables. Okay, so they have identical distributions. Yeah, so from one of my TA, during your midterm exam, I heard that one student asked the question about what is the meaning of identical. Okay? Identical means the same. Okay, identical twin means 쌍둥이인데 무슨 쌍둥이죠? 그게? 네, 일란성 쌍둥이. 그럼 일란성 쌍둥이 뭐죠? Okay, bonus point. Yeah, just kidding. Yeah, I have no idea. But anyways, I know at least identical twins means 일란성 쌍둥이. So identical means basically the same. Okay, same is the same as identical. Okay, so identical distribution means each of these random variable has the same distribution, but at the same time they are all independent of each other. So independent and identically distributed. So we usually call that as this IID. So back to this example, we basically have 10 different IID standard normal random variables. Okay? And then what will be the mean of Z1? The mean of Z1 will be 0 because it's just a standard normal random variable. And then Z2 will also have the mean of 0. But now, based on these 10 samples from IID, standard normal random variables, we basically take the square of it. Z1 squared, Z2 squared, and Z10 squared. Okay? And then, this is basically the meaning of chi-squared random variable. And here the degree is 10. Okay? So this degree parameter in the chi-squared distribution has this kind of meaning. So when thinking about the chi-squared distribution, you first think about the standard normal random variable, and then you just take the square of it and then sum them up. And then if you had 10 IID standard normal random variable, and then their squared sum will follow chi-squared distribution, where the degree V is set as 10. Okay? Okay, and then back to this. So, although it's a little messy, but the S squared, we actually defined the sample variance using this form, right? So what is it? It's the difference of actual sample. So we have 100 sample, and xi is ranging from x1 through x100, and then we take the difference between that and the sample mean among this 100 samples, and then take the square of it and then just sum them up, and then take the average of it in order to consider the variance. The average changes or variances. But instead of dividing it by n, we divide it by n minus 1. Okay? Because we have one less degree of freedom. But anyways, so we can just think about it as just n in order to compute the average of it. But when thinking about the chi-square distribution, we do not divide this summation by anything, right? So we just consider their summation with no denominator. Okay, so in order to make this guy look like chi-square distribution, we just multiply n minus 1. Okay, so that's why we see here n minus 1 as a kind of a multiplier. And then we divide it by sigma squared. And what is sigma squared? Sigma squared is the true variance value of your individual person's height. in your population. Okay, so that way, so we removed this part. Okay, so we removed this part, but instead divide this part by sigma squared. Okay, so we actually made this xi into kind of a standard normal random variable, because we subtracted its mean and then took the square of it and then divided it by the true variance. Okay, so in this process, this whole part is this whole part can be thought of as just one single zi and z2 and z10. And what was then? Yeah, what was it? z1, z2, z10 was again is a random sample from a standard normal random variable, okay, which has zero mean and unit variance, or the variance of 1. Okay, but here we take the summation of entire 100 samples. So intuitively, it seems to be following the chi-square distribution with the degree of freedom of 100. Yeah, but here in this case, the chi-square distribution will have the parameter of 99, which is 1 less than 100. And that difference, comes from the fact that we do not use, let's see, so we do not use the true mean value of xi's. Instead, we use our empirical sample mean, okay, in place of the true mean. Okay, so that way, let's see, this whole part, okay, this whole part does not, is not exactly the same as this Ci or Z1 or 2 and so on, okay? But the overall is approximately the same as Ci's, but when summing them up, so when summing all these 100 samples value of this, then it will still follow the chi-square distribution, but the degree gets reduced by just 1. Okay, so that is the main kind of takeaways of this theorem. Okay. 네.
V가 부과되는
가만히 있어 보자. 네, 맞아요. 이 경우요. 이 경우는 좀 달라요. 그러니까, okay, so in this slide, although it's a little bit messy, the upper part is all coming from the computation of sample mean, right? So sample variance. So we considered, or the starting point was the definition of our sample variance. But the bottom part is actually the pure original definition of chi-square distribution. So what is the definition of the chi-square distribution? Yeah, as I mentioned, you consider IID, standard normal random variables. So if you have 10 different samples from IID, standard normal random distribution, and then you take the square of it and sum them up, and then it will become chi-square distribution with the degree of 10. Okay, but in this case, in order to just contrast with this representation, in that case, suppose our random variable xi was following the normal distribution of mu and sigma squared. Okay, and then how can we change it to standard normal random variable? We just subtract it by mu, which is the mean value, the true mean, and then sigma, right? Which is a standard deviation. Okay, so this one becomes our zi, and here zi follows this standard normal random variable or distribution. So in this case, we can just so we suppose we have 10 different xi's, so x1 through x10, and then each of them will be transformed into z1 through z10 based on this standardization process. And then we just consider their squared summation. Okay, in this case, it's a chi-square distribution with the degree of 10. Okay, but in the previous case of this sample variance, or this kind of sample variance times n minus 1 divided by sigma squared. In this case, sigma and xi minus x bar n squared. Okay, so here if we just compare between this and this representation, then the only difference is that whether we use true mean or whether we use this sample mean. Okay, so if we replace this true mean with the sample mean, and then this guy will follow the chi-square distribution, but the degree, which is one less than the true number of samples, or the total number of samples. Okay. And also, here, one thing that I missed or forgot to tell you is that in this theorem, so when studying this theorem, we basically simplify the situation so that our xi's are all normal distribution. So in the case of a central limit theorem, we consider the sample mean, but the individual random variables was not necessarily the normal distribution. But here in this case, we basically think about the normal distribution only. Okay? We assume each of individual person's height is following the normal distribution. Okay, and then the difference between these two parts, whether using true mean or the sample mean. Okay, so previously in chapter 1 or 2, we talked about their kind of intuitive effect or kind of high-level effect. So by using the sample mean, let's see. So the difference between the xi's and the true mean, and then we now think about the difference between xi and sample mean. And usually, which one is larger than the other? Which one is the larger than the other? So, which one is larger? 1 or 2? 1 or 2? 1 again. Or 2. Yeah. So the first one is usually larger than the other. Okay. So I think I gave you this kind of example. So suppose the person's height has the true mean of 170 centimeter. Okay. So that is actually your true mean. But the surveying company A somehow, so each company obtained the 3 samples, but the first company, the company A obtained 171 and 173 and maybe 169. Okay, so in this case, what will be a typical way of computing the variance? It should be 169 minus 170, because the true mean is 170. So true mean is mu, and here mu is 170. So something like this. So this will be our typical way of computing the variance. Okay. But here in practice, practically we cannot know the true mean. So instead of using the true mean, when computing the variance, we actually replace this true mean with our sample mean. So what will be our sample mean? Sample mean will be 171, right? Which is just an average between these three numbers, right? And so instead of using the sample mean, the true mean, we actually use 171 and 171 and 171. And so it actually has an effect of moving this true mean into some sample mean driven by our data, right? So true mean can be thought of as kind of fixed value, regardless of what samples you have. But this kind of sample mean is actually fluctuating. So if you're the surveying company actually happen to obtain the samples generally larger than the true mean value, which is this case. So 169 and 171 and 173 is kind of a large, on average it's kind of larger than the true mean value 170, right? But still, when considering the variance, we have to use this fixed value of 170. But in this case, if we use the sample mean, and then this kind of sample mean is actually a shifted version to the right, because your data is actually more on the right side with respect to this true mean. Okay, so your mean value is actually fluctuating following your kind of the general data, right? So that way, this kind of difference. So here clearly this difference and their squared sum will be less than the case when using the true mean, right? So that way you are kind of underestimating the variance. Okay, so that's why we actually divide this guy by 3 minus 1. So n minus 1 comes from this kind of effect. So we kind of underestimated the differences, and so we divide them by smaller number. Okay, so roughly back to this chi-squared cases. So if we're going to use the sample mean instead of the true mean, and then we kind of remove we kind of reduce the degree of freedom when thinking about this chi-square distribution. So so if you have 100 samples and then compute their square the differences from the sample mean, and then it is same as the squared sum of 99 squared sum. Squared sum of 99 cases when using the true mean. Okay, so in the case of using true mean, you're kind of summing up 99 standard normal random variables. Okay, so that is actually the same as the squared sum of 100 standard normal random variables when using the sample mean. Questions? So I think, this is a quite important part. Okay, and although the slide didn't have the derivation, let's see. So let's check this kind of a high-level understanding in more detail. And the book has nice derivation on it. Let's see. Okay, this one. So suppose xi follows normal distribution that has mu and sigma squared. Okay, and then this guy, xi minus the true mean, and then divide it by sigma squared. Okay, so let's consider this guy. And then what will be the distribution for this guy? Chi-square distribution. And what is the degree? Degree is degree n or n minus 1? N. It is n. Why? We are using the true mean. Right? So again, the situation is xi is following the normal distribution that has mean of mu and variance of sigma squared. And then we standardized, right? And then took the square of it and then summed them up. And then this one is following the chi-square distribution, but and the degree is just an n because we use the true mean. And then we kind of manipulate this expression by just subtracting the sample mean and then adding this sample mean. Okay, and then these are inside of the parentheses, and so we just distribute it in this way. This one squared, and then the cross product times 2. Okay, so we have this part and this part and this part. But originally, this guy was inside, right? Because this summation is still in outside, it's located outside, and the cross product between these two will be inside of the summation. But this x bar minus mu is not dependent on I. So they are not changing depending on I. So we can factor it out, which is outside of this summation. And then this part will become exactly 0. So we will be left with only these two terms. Okay? So that's why we obtain this. And then, since we want to consider the chi-square distribution, we are dividing this equation by sigma squared. Okay, so sigma squared like this. So let's just remove this. Okay, and then we just change this guy into this part, and then change this guy. So this guy divided by sigma squared. Okay, and then this part is actually n minus n minus 1 times sample variance. So that was our definition of a sample variance. Okay, so this part is converted into this form, and this part is converted into this form. Okay, and then as I asked you guys about this question, the left-hand side becomes the chi-square distribution with the degree of an n. Okay, and then what will be this guy? What will be this guy? This guy is following standard normal distribution, because that is exactly the main main result from the central limit theorem. Or it doesn't even need a central limit theorem. But anyways, so you consider this a sample mean, and then the sample mean itself followed the normal distribution, right? And then it had the true mean of this guy and then the variance of this guy, right? And so this guy itself, this term itself is can be viewed as standard normal random variable. So it is like z 10 squared, okay? Based on this kind of example when talking about the chi-square distribution. So let's see. So again, looking at this equation, the left-hand side is chi-square distribution with the degree of n, and then among the two terms on the right-hand side, the second one is just this guy, which is just a squared standard normal random variable. And then when thinking about the meaning of the chi-square distribution, then it is like n number of summation of squared standard normal random variable, right? Just like this case. So we have 10 different standard normal random variable, and then square of it, and then sum them up, and then it becomes chi-square distribution, right? And among these 10, we have two terms, and then two parts on the right-hand side of the equation, and then one of them was just one single standard normal distribution. Okay, and then the rest of them will be, can be viewed as just n minus one number of summation of standard normal random variables. Right, so that's why we can view that as so that's why we can view this guy as n minus one number of summation of standard normal random variable, and thus it can also be viewed as chi-square distribution with degree of degree of n minus 1. Okay. Okay, so that is this theorem. Okay, then the next one is this T distribution. T distribution, So T distribution is kind of smoothly extended from this sample variance, which follows chi-square distribution. Okay, so here we consider this measure, right? So this measure is, so basically this part is just a z squared, except that instead of using true mean mu, we actually use the sample mean, right? But here in this case, we are using the true variance, right? So true variance of our individual random variable. But this guy may not be known either, right? So in practice, we do not know the true mean, but at the same time, we do not know the true variance of your distribution. And so this distribution, this true variance value can also be replaced by our kind of estimated version of this true variance. And what is that? And that is our sample variance. So we can change that part into sample variance, and then that actually further complicates our situation. But in that case, that distribution is actually following this kind of T distribution. Okay, so that was kind of a high-level kind of story about how we can extend from this chi-square distribution into the T distribution. But let's continue it next time. And that's it for today. Thank you.
죄송한데 한 가지만 얘기할 거 있어서
끝나고 할까요?
이번에 정보대학 3대 학생회장단 부후보랑 16학번 채점지입니다. 다음 주 선거에 앞서서 몇 가지 공약이나 그런 거 말씀드려야 될 것 같아서 이런 자리에서 말씀드리는데, 일단 공약은 여러 가지가 있는데 크게 두 가지로, 첫 번째 올해부터 실시하던 카카오톡 옐로우 아이디 활성화랑, 두 번째로 올해 정통대와의 통합인데 좀 더 자세한 부분들은 정보관 1층 로비에 걸려 있고요. 다음 주 월요일하고 화요일날 정보관 1층에서 투표 있으니까 많이들 투표해 주셨으면 좋겠습니다. 감사합니다.
그 우리가 PDF를 통해서 probability를 계산을 할 때 보면 true distribution으로 계산하는 게 정확한 값이잖아요. 근데 n-1 degree of freedom으로 그냥 그런 분포를 갖고 있다 하고 끝인가요? theorem.
네. 그러니까 그게 뭐냐면 이제 카이스퀘어 디스트리뷰션은 그러니까 뭐 베리언스가 예를 들면은 얘는 뭐 3이라 그러고요. 얘는 8이라 그래요. 그러면은 과연 얘네 둘이 그러니까 예를 들면 컴퍼니 A에서는 뭐 동작구에서 50명을 뽑았고 컴퍼니 B에서는 뭐 사당 뭐 하여튼 사당동에서 둘 다 똑같네요. 하여튼 뭐 다른 지역에서 뽑았다고 해봐요. 그러면 얘네들이 같은 디스트리뷰션이라면 같은 디스트리뷰션이라는 가정에 출발했으면 여기서 각각 다 계산한 샘플 베리언스도 어느 정도 그 같은 카이스퀘어 디스트리뷰션에서의 어떤 뭐 거기서 이제 출발한 혹은 거기서 이제 나타나는 어떤 값들일 거잖아요. 근데 이게 뭔가 같은 디스트리뷰션이라고 가정을 해갖고 이거를 그래서 같은 카이스퀘어 디스트리뷰션 내에서 뽑혀진 애들이라고 생각을 하고 얘들 바라봤더니 그게 안 맞는 거예요. 너무 뭔가 멀거나 이렇게 되면 이제 애초에 이제 그때랑 비슷하게 이제 애초에 그런 가정이 틀렸다는 거, 어딘가에서 뭔가 가정의 어떤 부분이 잘못됐다는 거. 그래서 그런 어떤 가정, 그러니까 그 가정이 맞는지 안 맞는지를 검증하기 위해서 사용하는 기준이 되는 디스트리뷰션이 뭐냐는 게 바로 이 샘플 베리언스 같은 경우는 이 카이스퀘어 디스트리뷰션을 따르기 때문에 카이스퀘어 디스트리뷰션을 사용을 해서 그런 확률이라든가 이런 것들을 계산을 해야 됩니다.
아까 이 식에서
네.
이 왼쪽에 n 그 degree of freedom이 n라는 건 이해가 되는데
네.
이 부분이 잘 이해가
이 부분은요. 그러니까 x 바가 뭐냐면 센트럴 리밋 티어럼에서 x 바가 결국은 이제 그 노멀 디스트리뷰션을 따른다고 했었고요.
네.
그리고 x 바에다가 x 바는 그러니까 뮤라는 평균을 가지고 그러니까 원래 xi들 그 짜잘한 xi 하나하나들이 갖고 있던 평균값이 얘 x 바에 혹은 이 샘플 민의 평균이 돼요. 그 다음엔 걔의 베리언스 이게 된다는 건 이제 우리가 알고 있죠. 그러면 x 바가 결국은 이 표현은 뭐냐 하면 어떤 x 바를 우리가 저기 스탠다드 노멀 랜덤 베리어블이 있을 때 걔가 이게 z가 있어요. z가 이제 뮤고 이제 0, 1 제곱 이런 놈이 있어요. 그러면 이제 g 제곱이라는 어떤 새로운 랜덤 베리어블을 이제 생각을 해봐요. 그랬을 때 이제 지금 요 놈도 결국은 즉 뭐냐 z를 어떻게 정의를 하냐면 시그마의 스퀘어 루트 n의 이제 x bar 마이너스 뮤라고 정의를 해요. 그럼 이거는 정확하게 이걸 따르죠. 스탠다드 노멀 랜덤 베리어블을. 그죠?
네.
오케이. 그러면 이거에 결국 z 제곱이 여기 자리에 들어가 있는 거죠.
네, 그렇죠.
그죠?
네.
그러니까 이거는 뭐냐? 결국은 이게 뭐 x바의 의미고 뭐고 다 떠나서 얘는 뭐냐면 스탠다드 노멀 랜덤 베리어블을 하나를 잡아다가 그거를 어떤 형태로 제곱을 한 놈 값이란 뜻이에요.
네,
그죠?
그렇죠. 값이죠.
그죠? 그러면 이 카이스퀘어 디스트리뷰션은 뭐 이렇게 이 z들의 썸으로 구성되어 있는 놈이라고 우리가 그 어떤 정의를 생각을 했었잖아요. 그러면 여기 부분은 지금 잘 모르지만 여기에 z 하나가 있어요. 그리고 이거는 z들이 총 10개였다 그러면 n이었다면 n개가 다 더해진 형태로 생각을 해볼 수가 있었는데 이거는 이게 복잡한 형태이긴 하지만 이건 잘 뭔지 모르겠지만 여기에 z가 하나가 있는 거예요. 여기 z가 n개가 있었고 여기 z가 하나가 있다. 그럼 z제곱이요. z제곱이 이제 총 n개가 더해져 있고 여기 z제곱이 하나가 있다. 그럼 여기에는 z제곱이 n-1개가 있다라고 생각을 해볼 수가 있는 거죠. 그렇기 때문에 이 부분을 그러면 이제 그 n-1개의 z제곱들이 이제 합해진 형태로 보고 걔가 여전히 카이스퀘어 디스트리뷰션이 돼 디그리가 하나 줄어든 형태로 이해를 할 수가 있다는 뜻이에요.
이게 무슨 말이야?
알겠습니다.
강의 저번 거.
네. 오늘 올려줄게요.
오늘.
네.
이게 어디서 이거야? 외국